My name is Masashi Yoshimura, and I'm from Entity Corporation in Japan, and I represent elfconv AOT compiler that translates Linux AArch64 ELF binary to WebAssembly. Okay, so first, I will briefly explain the features of Wasm. Wasm is a virtual machine instruction set, and currently this is used on servers as well as browsers in production environments. And compared to existing applications, there are mainly two advantages: portability and security. And in portability, Wasm enables us to run applications on both browsers and servers without modification. And of course, Wasm doesn't depend on CPU architectures, so that we can run Wasm applications on computers with various CPU architectures without modification. And in security, in the case of outside browsers, Wasm is highly isolated from the host kernel by WASI. And also, Wasm has a Harvard architecture design, so the memory of the Wasm instance is separated into Liner data memory and code memory. And the code of Wasm can access only to Liner data memory, and that which increases security. However, there are some limitations in the capability of applications. First, Wasm can jump to only the codes that are determinable at compile time. In other words, it is impossible to indirectly jump to the code generated in the data memory. And second, WASI implementation doesn't cover all POSIX APIs. For example, fork and exec and so on. And so when you develop Wasm applications, you should consider the limitations when you use WASI runtimes. And so many programming languages support Wasm. For example, C, C++, Rust, Go, and so on. However, it isn't easy to build Wasm in some cases as follows. Mainly, there are three such cases. First, the programming language that you want to use doesn't completely support Wasm. Many major languages have begun to support Wasm, but only a limited number of languages are available in production environments now. And also, you could use the awesome Wasm language repository as reference information. And second, binaries are available, but the source codes of the binaries are not available. Recently, the number of open source programs has increased, but several programs are still not published. Third, the case of being difficult to build the source code. If the dependent libraries are not public or unavailable for some reasons, it is difficult to generate the Wasm binary of the target program. Considering these facts, I propose running binaries on the Wasm environment. Okay, so next, I will show existing projects that run Linux binaries on Wasm. The first project is TinyEmule. This is the x86 and RISC-V emulator available on the browser, and Linux kernel can run on the browser with TinyEmule. And the second project is Continental Wasm. And this enables us to run Linux kernel and content runtimes with emulators compared to Wasm. For example, TinyEmule. And this can run containers without modification both on the browser and WASI runtimes. However, these projects use VM on emulators, possibly incurring large performance overheads. Considering this fact, we propose a method of AOT compiling Linux binaries to Wasm. So I propose elfconv and AOT compiler from Linux elf binary to Wasm. In this project, first, the input is elf binary, and we compile the binary to LLVM bitcode by elfconv lifting module. And second, we generate the Wasm binary by existing compiler collections, for example, emscripten or WASI SDK, while compiling the LLVM bitcode and statically linking the elfconv runtime. And elfconv runtime includes Linux system calls emulation and so on. Okay, so next I will show the demo of elfconv. The demo program is a neural network for training the emlist database written in C language, and this demo program is public on GitHub. And emlist database is a large popular database of handwritten digits for mainly machine learning training of image processing systems. And many handwritten digits, as shown in this figure, are included in the database. And you can check the accuracy of your model using it. And so this program keeps training the emlist database and keeps outputting the average loss and accuracy. Then I will show the demo, but I will show a video of the demo for reasons such as it takes a few minutes to translate by elfconv. Okay. So this is a video of the demo, and you can see that the elfconv container has already started. First, I will show how the emlist program is executed. And the directory is examples emlist neural network plain C. And we can build this program by make command. Okay, so and the generated emlist binary is statically linked AArch64 ELF binary. And then I will execute the emlist binary. Okay, so and you can see two numbers, average loss and accuracy. And you can see that the average loss continues to decrease and accuracy continues to increase. Okay. Okay, so second, I will translate this emlist AArch64 ELF binary to Wasm binary. And we can try elfconv translation in the elfconv bin directory by elfconv.sh file. Okay, so I will translate and target this Wasm first and execute elfconv.sh and examples, emlist neural network, plain C, and emlist. Okay, so now elfconv translating the elf binary to Wasm, and it takes a few minutes to translate. So I proceed with the video. Oh, sorry. Okay. Okay. At this time, translation has finished, and the exit to Wasm was generated. Yeah. So, and by the way, you can see it takes 1 minute 47 seconds to translate. So then I can execute this Wasm file by WASI Runtime, but it is very slow to execute by interpreter mode. So I will AOT compile this Wasm file by WasmEdge runtime. So now WasmEdge AOT compiles the Wasm binary. Okay, so and it takes and it takes a few minutes to AOT compile. So I'll proceed with the video. Okay. Oh, okay, sorry. Okay. Okay, so and now AOT compilation has finished, and it takes 1 minute, 54 seconds to AOT compile. Okay, finally, I can execute the Wasm binary as follows. So AOT underscore exit Wasm is the target Wasm binary. Yeah, great. So the speed is a little slow, but you can see that the training is in progress. And if I proceed with the video, you can see that the training process is correct. Okay, so this concludes the demonstration. Let's return to the presentation. Okay. Okay, so I will explain the details of the translation of elfconv. And Linux elf binary has two major sections, data sections and code sections. So we should convert these sections to the LLVM bitcode. And as I explained earlier, the elfconv lifting module compares the elf binary to LLVM bitcode, and it consists of two modules. And the first module is elfconv lifter. This passes the elf binary and allocates the memory for the data sections of the elf binary on the LLVM bitcode. And also, the elfconv lifter detects the function of the elf binary and inputs those functions to the second module remill. And remill is a library for lifting machine code to LLVM bitcode. And remill is an open source project of lifting bits organization and supports several CPU architectures. For example, AArch64, SPARC32, and x86, and so on. And so remill receives the function from the elfconv lifter and converts every function of the elf binary to the function of the LLVM IR. For example, as you can see in the figure, underscore stat function on the elf binary is converted to underscore stat underscore lift function, and underscore fun1 function is converted to underscore fun1 underscore lift function in the LLVM IR. Okay, so next, in converting the LLVM bitcode to Wasm, statically links the LLVM bitcode and elfconv runtime. elfconv runtime includes the runtime memory of the stack and heap area of the elf binary. And also, elfconv runtime includes the program of Linux system calls emulation, and existing compiler, emscripten or WASI compiles these two modules to Wasm. Okay, so in the Linux system calls emulation, there are two ways of implementing the emulation. The way of implementing depends on the libc implementation. In pattern 1, if the libc implements the target system call, elfconv just uses the libc function, as shown in this figure of the right system call. And in pattern 2, if the libc doesn't implement the target system call, elfconv suit implements the system call as shown in this figure of BRK system call. And as you can see, this call doesn't call the BRK function. Okay, so next I will show the performance of the execution speed of the generated Wasm binary. Okay, so I use the Rimpak benchmark program for benchmark tests. And Rimpak is a program to evaluate 64-bit floating point operations per second. And we use the Rimpak program written in C language as benchmark tests. So we generated the target ELF binary by cron. And so I will show the methods to measure the performance. And elfconv is a technique of binary translation between different binary formats. So we compare the execution speed of running the binary of different architectures from the host environment. And currently, elfconv supports translating only AArch64 ELF binary. So we choose AArch64 as a target binary architecture and x86-64 as a host environment architecture. And we use three methods for measuring the performance of the execution speed of the Rimpak AArch64 ELF binary. And the first method is QEMU emulation. In this method, we execute the AArch64 ELF binary by the QEMU user emulation from AArch64 to x86-64. Another second method is AOT compilation from AArch64 to x86-64. In this method, we use elfconv and current to AOT compile to x86-64 ELF binary, and we directly execute the ELF binary on the host environment. And the third method is AOT compilation from AArch64 to Wasm. In this method, we use elfconv and WASI to AOT compile to Wasm binary and execute the Wasm binary by WasmEdge runtime. Furthermore, in the third method, we AOT compile the Wasm binary by WasmEdge and execute the binary not interpreter mode. Okay, so here are the measurement results. And Rimpak benchmark evaluates 64-bit floating point operations per second. So the number is larger, the execution speed is faster. As you can see, in the current implementation, comparing methods 1 and 2, the AOT compilation is a little faster than QEMU emulation. And compare methods 1, 2, and 3, the performance of method 3 is slower than the method 1 and 2, and method 3 is 0.34 times as fast as method 2. And by the way, I measure the Rimpak program performance compared from source code, not binary translation, and found that the performance of the Wasm Rimpak binary is 0.51 times as fast as the performance of the AArch64 ELF binary. And as this result shows, since Wasm is slower than native in the first place, so I consider that it is inevitable that method 3 will be slower than method 1 and 2. Okay, so I will show the future works. And first, we will append the system calls emulation. And now, elfconv implements a part of system calls, and a lot of system calls are not implemented. Specifically, when targeting Wasm as output binary format, some system calls are difficult to implement. For example, fork, exec, and so on. And second, supporting dynamic linking. elfconv can compile the static linked elf binary, but dynamic linking is an important function, and I will support it in the future. And third, I will make the generated binary and LLVM bitcode more efficient. In the current implementation, the ELF binary is a little faster than QEMU emulation, but I want to generate the binary or LLVM bitcode that runs considerably faster than QEMU emulation. So, and also, I want to make the translated Wasm faster. Next, we will enable us to translate the ELF binary of the other CPU architectures. And now elfconv can translate only AArch64 ELF binary. Yeah. Next, we will support the output of other binary formats. Currently, elfconv supports the output of only Wasm and ELF x86-64 binary. Okay, so next, in the future, we will continue to develop elfconv and want to spread the usage of elfconv and integrate it into the existing WasmEdge system. So I hope that you will not hesitate to throw your issues and PRs to us. So next, I will show related works. And elfconv is a successor to my AOT project. And this is an experimental AOT compiler that translates Linux RISC-V32 ELF binary to several binary formats. And I refer to some implementation of my AOT project for elfconv developing. Okay, so that concludes my presentation. Thank you very much. Okay.
Have you ever compared the performance of an elfconv binary versus container to Wasm?
So yes, yeah. So it is a future task, and in the container to Wasm, there is not the performance results in the container to Wasm now. So yeah, I cannot compare the performance now between the elfconv and container to Wasm. Okay. Okay.
So you mentioned like you have in the future work to make faster the WebAssembly target compilation, but do you have already some ideas about how to improve the performance?
Sorry, once again, sorry.
Yeah, you mentioned that the future work for this project is to make the WebAssembly target faster. So do you have already some ideas about how to make this performance improvement?
The question is about how we can compare. How we can faster the generated Wasm binary run. So yes. So and in my idea. The generated LLVM bitcode in the current implementation is a little long and not optimized. So one method to optimize one method is to optimize the LLVM bitcode generated. Yeah. So, thank you. Okay, thank you.
So, on WasmEdge, did you enable AOT on that side as well? That would be a performance improvement, I guess.
Sorry, so could you please speak a little slowly and in simple words?
Okay, so you mentioned WasmEdge as the target runtime.
Yeah.
And WasmEdge has an option to enable AOT compilation.
Yeah.
Is that enabled in this case? This could be an improvement for performance, I guess.
Yes.
So you would end up having binary that runs machine code.
So in the performance of the Rimpak program, I already LT compiled by WasmEdge runtime, and I measure the performance of the LT compiled Wasm binary by WasmEdge. Sorry, it is not answer. After the presentation, could you explain again? Sorry, thank you.
You mentioned that syscalls and dynamic linking are two things that aren't supported. Are there any constructs expressed in ELF besides that are difficult to translate to Wasm?
So the question is about dynamic linking. The support of dynamic linking is difficult to Wasm.
No, just are there any, besides the syscalls, the missing Linux syscalls like fork and exec, are there any constructs that are expressed in ELF but cannot be expressed in Wasm today?
Sorry, could you speak sorry, in simple words?
Yeah. What other incompatibilities besides the syscall, besides the missing syscalls, did you experience or run into?
Did you experience? Sorry, I don't understand the question. So after the
That's
presentation.
okay. Sorry.
Sorry.
I'll ask.
Again after the presentation. Thank you. Sorry.
Okay. Thanks.
So much.
Hi, thank you for the talk.
Hey.
Can you compare the size of the binaries, both with x64 and with Wasm, and how do they compare? Is Wasm a bigger file size?
So the question is about the image size of the generated Wasm binary between the generated Wasm binary and the Wasm binary compiled from source code.
Yeah, great.
Yeah. So thank you. So I think the generated Wasm binary basically very large, and for example, in the Rimpak benchmark program, the generated Wasm binary is maybe 17 megabytes. So, but the Wasm binary compiled from source code is about 100 kilobytes, maybe. So I think the generated Wasm binary is very large. So yeah, that is a problem to solve.
Yeah, thank you.
Thank you. Okay. Thank you.